Hey everybody, today we're going to be talking about section 5 or 3.5, which is population growth and resource availability. Now the learning objective for today is that you can explain how resource availability affects population growth. Some of the essential knowledge that you're going to gain is some of the different factors that impact population growth, such as like resources and the stuff that they have available, and the different types of rates of growth that these can cause in our different populations. And we're going to look at like some of the actual calculations of how to figure out the growth that's happening. The suggested math skill for today is that, or the suggested skill is mathematical, that you'll be able to apply appropriate mathematical relationships to solve a problem with work shown by doing stuff like dimensional analysis. All right, so first we're going to start talking about population characteristics and basically the different ways that you can characterize population. So the first is going to be by size, and typically, mathematically, size is going to be indicated by n, and size is going to be the total number of individuals in a given area at a given time. Now, something to remember about larger populations is they tend to be safer from population decline, just due to the fact that there's a lot of them. So it's more likely that more of them will be able to reproduce and continue the growing population. Another way that we can characterize populations is density, which is going to be the number of individuals per area. So for example, if there were 12 panthers per square kilometer, that would be an example of how to show density. Now, some things to remember is that high density actually is not so good because there's going to be higher competition. There's more in the area that are competing for the resources. You can also have more of a possibility of disease outbreak because they're all close together, so diseases are going to spread more rapidly. And there's going to be more possibility of depleting food sources because there is a limited amount of food, and the more organisms you have, the less there is to go around. Now, we also can talk about the distribution of populations. So this is going to be how individuals and populations are spaced out compared to each other. And there's going to be three different ways that we typically see distribution in populations. The first is going to be random, which you can see up here in the top right. If you look at the diagram here of where the organisms are going to be present, this specific example is going to be like trees. You're going to see that they are randomly distributed. There's no uniformity to it. Some of them are in clumps over here. Some of them are spaced out over here. So it is random in the way that they're distributed. The next is going to be uniform distribution, which we typically see in territorial animals. So the example that you see right here is going to be with these seabirds on a cliff. And they're pretty uniformly, evenly distributed. And this is going to make it so all of them have their own little space and territory, but they're kind of maximizing the space that's available to them. And then the last is going to be clumped, which we tend to see with herd or group animals. So on the bottom here, we see this example with meerkats. And meerkats actually have like individual little mounds or burrows, and you're going to have the families grouped in that way. So you can see like that. Or if you have ever driven by a field of cows, you may notice that they're kind of grouped together in different groups throughout the field because they're herd animals, and that's going to be a typical distribution that we see for them. So next we're going to talk about population characteristics and some of the growth factors that can impact how this population is going to grow. Now the first is going to be the sex ratio, and sex ratio is just the ratio of males to females. Now, the closer that it is to about 50-50, the more ideal for breeding, usually. There are some examples, for example, like walruses are going to have one male for a harem of females, but typically you're wanting about 50-50 so that you can have like even pairs for breeding. Now, if we ever have a die-off or a bottleneck effect, this can lead to skewed sex ratios. Maybe there won't be enough females, which would be catastrophic because the females are the ones who tend to reproduce or be the ones that bear the children. And so a skewed sex ratio is going to limit population growth. So that ideal sex ratio is going to be beneficial for population growth. And there's going to be different factors that we can have for influencing the population growth based on size. And it is important that you know these different types of factors. You will be asked this on the AP exam. I will ask you this on tests because it's important. So the first is going to be density-dependent factors. And these are factors that influence the population growth based on the size of that population. So for example, like food, competition for habitat, water, light, even disease. So when we're looking at like resources, the more organisms you have, the less resources they're going to be. And so it's density dependent because it depends on the population for how much those resources are available. And then disease is if you have a lot of them in one area, that disease is actually going to spread faster and it's going to be more impactful if there's a large population. So we also say that that is density dependent. And all of these things are going to limit the population growth based on their size. So for example, smaller populations are not going to experience these factors. If you have a small population, you got enough food to go around. But larger populations are going to experience these factors. And the other type is density independent factors. And these are factors that influence population growth independent of the size, so regardless of the size. So an example of this might be a natural disaster like a flood, a hurricane, a tornado, or fire. It doesn't matter how big or small the population is. The natural disaster is going to limit a large population or a small. Regardless, if a hurricane hits, you're going to be negatively impacted by that, and it had nothing to do with the original size of your population. It just happened. So here's going to be a pretty famous experiment. I think it was done by a Russian scientist that is going to prove that food is a density-dependent factor, and it's also a limiting resource. Now, it might feel like this is pretty obvious, like you would just assume food is a density-dependent factor. It is a limiting resource. But in science, you always got to have science experiments to prove this. You don't ever want to just make assumptions. And so this is going to be an experiment where this scientist took some different single-celled organisms. They're called paramecium. They're individual little organisms here. And at first, he gave them low food conditions. And so if you look, the red line up here on top is going to be one of the paramecium species. The bluish green one is going to be a second paramecium species. Now, when they had a low food supply, at first they grew really rapidly, and that's going to be because there was still food available. But then we're going to see that they started to plateau, and that's going to be when food was no longer abundantly available. So you started having some competition, and only a certain amount of populations could thrive here. So that's the first half. The second half of this experiment, he gave a high food supply with twice as much food. And you can see right here that the red paramecium species grew to 195 organisms. And then this bluish green paramecium species grew to 137. And so both of the populations grew almost twice as large, and they did eventually have that plateau because, again, you are going to run out of food eventually. But this experiment proved that food was going to be a density-dependent factor, and that the more food you had, the larger the population could be. So now we're going to look at some graphs, which these are important graphs for you to be able to tell. There's two different graphs that we look at when we talk about population growth. And the first one we're going to see on the left-hand side here. This is going to be an exponential growth curve. We also call it a J curve because it's shaped like a J. And this is what we're going to see when populations are having their maximum potential growth with no limiting resources. And so it's just going to be skyrocketing. You can keep reproducing over and over and over because you've got all the resources you need. Now, typically when we're seeing this out in the natural world, this is possibly going to be occurring initially, but eventually you will have limiting resources. You're going to have competition, food, disease, predators, and eventually we will have a slow growth, and we're going to be able to limit the population to its carrying capacity. So you only see biotic potential for a period with populations, but if we're just looking at the beginning and this is what we're seeing, we would say that it is an exponential growth curve. Now, if you remember biotic potential, this, when we talked about it a few notes ago, that's going to be when organisms are reproducing at their maximum rate. So biotic potential is going to be when we're seeing exponential growth. Now, the second graph that we have here on the right-hand side, this is a logistic growth curve. It is also called an S curve because it's shaped like an S. And this is going to be your kind of realistic over time graph that we're going to be seeing with populations. So initially you are going to have this rapid growth like we saw with the exponential growth. And this is because you are at this point going to have unlimited resources. You're not limited by the population size. Then you're going to end up having limiting factors, and that's going to limit the population to its carrying capacity. So you're going to see it kind of level off around the carrying capacity right there. And that's going to be a logistic growth curve. So now this is going to be how you calculate population change, because this is something that you're going to need to be able to do. It will probably show up on your AP exam, but it's also just being able to kind of know what influences the changing numbers of a population. And when we're generally going to be looking at this, you're going to have the inputs are going to increase population and the outputs are going to decrease them. So inputs are going to be immigration. When organisms immigrate, they come into a population, and births, because births are going to add individuals. Now, things that take out is going to be emigration, where they move away, or deaths, where you're going to be losing those organisms that died. And so this is going to be the equation for calculating population change when we're just looking at like the population numbers. So population size is going to be equal to immigrations plus birth minus emigrations plus death. Now, when you're considering the population size, you always want to consider the original population size in your calculation, because that's what you're going to be adding this calculation to. So for example, if we were to have an elk population of 52 elk that has 19 births and 6 deaths in a season, and 5 new elk immigrate to that herd, and then 0 elk emigrate from that herd. So I'm going to wait a moment with this video. I recommend you pause it, try to do this math on your own so that you can see if you were able to calculate this correctly. All right, I'm going to assume that you paused the video and now you're ready to see the answers to make sure that you did it right. And that is going to be doing the math here. So if we had 5 immigrations plus 19 births, it's going to be in the first parentheses, and you're going to subtract. We had 0 emigrate, but we had 6 deaths. So when you do all that out, it's going to be plus 18 elk. So remember, our original population was 52 elk. So when you add 52 plus 18, you are going to now have 70 elk as the new population size. Now, you are going to have to also calculate population change in the form of a percent. So the last time was just going to be showing you like the actual numbers of the population. But if we're wanting to know like population growth as a percentage, which is more commonly how we tend to look at this, this is going to be your equation for doing that here. So population change percent is going to once again be that immigrations plus births minus emigration plus deaths. Ooh, sorry, that should say plus at the next one there. Is going to be the divided by the total population, and you're going to multiply that by 100 there. So for example, if we were to have this situation where we have a rabbit population of 60 rabbits that has 12 births and 8 deaths in a season, and we have 2 new rabbits immigrating to the herd and 4 rabbits emigrating from the herd, I want you to do the math here so that you can see if you're able to do it correctly. So I'll have you pause the video here before I give you the answer. And I'm going to assume you pause the video, so I'm going to give you the answer here now. All right. Now the example, the equation is right. So just make sure you fix, it should be emigration plus death, not emigration minus death. But it's going to be 2 plus 12 minus 4 plus 8 divided by 60, which was the original population, and you multiply that by 100. And our percent change in the population is going to be 3.33%. So what we would say is this population grew by 3.33%. All right, this is going to be your FRQ practice for 3.5. So I want you to calculate the population size of a 14 wolf or a wolf pack that has 14 individuals. It's going to experience 5 deaths, 3 births, and 4 new wolves are released into the pack from a nearby wildlife sanctuary. So do the math here. You're going to be calculating the population size, so the actual like numbers. You don't have to do the percent with this one. And that is going to be your FRQ practice for 3.5. Those were your notes on 3.5 about population characteristics and growth.